It's the New Year's edition.
There you go. Friction. Friction is a force that occurs when two objects try and slide across each other, and it resists sliding. It actually occurs if you zoom in on any object, even if it looks really smooth. You'll see when you zoom in that there are actually jagged cracks and crevices and hills and valleys. And when those two surfaces with their jagged cracks and crevices and hills and valleys rub across each other, they jerk along each other. We call that force friction. It's the interlocking of molecular hills and valleys between a surface and an object. So although surfaces may appear smooth on the atomic scale, they are not. Friction resists sliding, and because of that, it can resist motion, like when you're trying to push something across the floor, a heavy object. It can also create motion. We said that when you walk, it's friction that pushes you forwards because your feet push backwards. Or when you drive, it's friction that pushes a car forwards because the tires push backwards. So we can't just generically say that friction opposes motion. All we can say is friction resists the sliding between two objects, and that can sometimes create motion, that can sometimes prevent motion. In fact, later on, Curtis will be saying that there's technically two different types of friction. Example 1, I wrote, draw the direction of friction in each case. So in situation A, sliding block, my example for this is if any of you have ever been in gym and slid the benches across the floor. There are those sliding benches on the back wall against the gym. You slide them across the floor. You feel a force pushing against you. So if we were sliding the benches to the right, which way do you think friction would be acting? To the left. And my abbreviation for friction is traditionally FFR. I don't know why I put the R. Kids have asked me over the years, why don't you just go F, friction? I don't know, but for some reason, sometime in high school or in college, I just started writing F. You don't have to. It's me. What about for a car speeding up? Well, you really have to think about what's happening. The most common mistake I see, and in fact, I've even seen teachers make this mistake, is they say, oh, the car's going forwards, don't write this down, so friction must be that way, don't write that down. Actually, you have to look at the tires. So the tire is rotating this way. Right where the tire meets the road, the tire is actually pushing backwards. And now we have a Newton's third law, forces come in pairs, kicking in. The tire pushes backwards against the road. What does the road do? Push forwards against the tire. And what force is that? That would be the force of friction. For a car going forwards, it's friction that pushes it forwards. That's why you can't drive on ice. Because the tires, if it was the tires that made it go forwards, you'd be able to drive on ice because the tires are still there. What's changed? Friction. Friction. The same with when a car slows down. So when a car slows down, your brakes exert a force on the wheels, and therefore your wheels exert a force that way against the road. They actually push forwards against the road. And again, Newton's third law, forces come in pairs, kicks in. The tires push forwards against the road. What does the road do? Push backwards. For a car slowing down, friction acts that way. And again, that's why it's tough to brake on ice. How do we calculate friction? Well, I've mentioned ice and I've mentioned gravel. I guess it depends on the type of surface. In our equation for friction, there should be, Manny, some way that some number, some symbol that shows how rough the surfaces are. And I would think the number would be really small for ice and really big for sandpaper. And there is. But I've also noticed when I push something across a floor, the heavier an object is, the tougher it is to slide. It's pretty easy to slide, for example, this little foam dice across my linoleum floor. I can do it with a couple of fingers. It's much tougher for me to slide with 2 fingers the lab table that Dane is at. I'm pushing and it's not moving. So maybe it also depends on an object's mass? No. At first, Atla, you might think that, but we're going to be even fussier. So here's what we're going to say. The amount of friction depends on two things. The first is the type of surfaces that are in contact with each other. And we represent this by, here's a word you want to underline because I'm going to use it like crazy, the coefficient of friction. Now the coefficient of friction, it's a symbol, and the symbol is a Greek letter that looks like that. It's the Greek letter mu. As a matter of fact, it looks just like this. What's mu, Mr. Dueck? I don't know. What's mu with you? No? Okay. What does a Greek cow say? Mu. Right? Whatever dumb joke you want to come up with. It's where our letter M comes from, by the way. You can almost see a lowercase m kind of coming out of here. It's a symbol, just like A, just like V, just like F. We've been using symbols, mostly English letters. This is the first time that we've run out of letters. We're having to pull out a Greek letter. What does it stand for? All it is a decimal. And the bigger the decimal, the stickier the objects are in relation to each other. The more friction force there's going to be. The smaller the decimal, the slipperier, the slicker the objects are in relation to each other. It has no units. So if you ask me, what do we measure mu in? Nothing. It's a unitless number. In fact, it's a ratio. So I gave you a couple of examples. If mu is large, there's lots of friction. If mu is small, there's going to be little friction. Steel and ice, nearly zero. That's why when you push yourself on your ice skates, you can glide for quite a while. In fact, what's slowing you down more than anything is air resistance hitting you like a parachute. If you did it in a vacuum, you would glide for you'd die, sorry, but with no air resistance, you would glide for quite a while, far further than you think. You would glide for quite a while before you came to a stop. Rubber has a high coefficient of friction, has a high mu. That's why we use it for tires. So rubber on concrete, about 0.75. Although when it rains, that drops to about 0.35. It drops dramatically. When it snows, it drops even more. And we'll talk about, Kai, why driving in the rain and driving in the snow, it has nothing to do with how good a driver you are. You can't beat the physics. Slow down. Because I always have someone go, I'm a good driver. I can drive fast in the snow. I'll hopefully convince you that it has nothing to do with your skill level. It's the laws of the universe. So friction depends on mu, the coefficient of friction. What else does it depend on? Atla, I said heavier stuff is tougher to slide, except, I'd like to show a little demonstration here. Pause the video for a second. So if we go to the very, very bottom here, we'll come back up in a second. But as an equation, we say this. Friction, which is a vector, is equal to mu times the normal force. Now this is kind of strange here, Manny. You'll notice I drew a vector on friction. I didn't put one on the normal force because the normal force points up and the direction of friction is always parallel to the surface. So this isn't, we're actually doing something called a cross product, which you'll look at in first year university. I'm sneaking something in. I'm just saying, don't freak about the direction. Friction's going to be in the opposite direction that you're trying to pull something, even though the normal force points perpendicularly to it. Don't freak out. Where mu has no units and it's the coefficient of friction. Kids often think that mu is the force of friction. No, 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 it's not measured in newtons. And Fn is the normal force. Let's come back up here. Okay? So I talked about the benches in the gym. Let's suppose that you're pushing one of the benches in the gym, like example 2. So example 2 says, consider the block below. Instead of a block, let's think the benches in the gym, which is being pulled by student number 1 across a rough surface. Let's think the gym wooden floor. At U, constant speed. Suddenly, student number 2 pushes down on the block with a force F. You know what? Let's change that. Suddenly, your friend comes along, jumps into the air, and lands on the bench. I'm sure you've seen that happen before when someone is trying to move the benches. One of their idiot friends comes along, I'm going to sit on the bench like that. If student number 1 maintains the same force as before, what happens to the weight the normal force, the friction force, and the motion of the block.
Increase.
Let's do one at a time. And you know what? Let's call weight A. You know what? Let's go like this. A, B, C, D. So, A. Weight. Now, I snuck this in last lesson and the lesson before. When we use the word weight in physics, that means something very specific. Does anybody remember? I know it was pre-Christmas. You're close, but not close enough that I can say. Weight is a specific force. McKinley. Yes. When you see the word weight, that equals mg. So here's my question. In this situation, only looking at the bench, did the mass of the bench increase? No. Did G increase? No. And this goes back to why at we said, although we might think that it's nicer to look at the mass of an object for friction, the weight actually isn't the force that I should be looking at, because this remained constant. That didn't change. Dane, what's the second thing they want me to look at?
Normal force.
Ah. What happened to the normal force when your friend hopped on top of the bench? That's the force that increased. F, and how about up arrow for increased, down arrow for decrease? And because friction is mu times the normal force, what can you say happened to the force of friction? Now, what word did I underline in the original paragraph?
Coefficient.
No.
Constant.
Okay, constant speed. So what that meant was, if friction was 10 newtons, you were pulling at exactly 10 newtons. Constant speed. What just happened to the force of friction now? What did you say happened? So what's going to happen to the motion of this block? Not just that. It has to stop, because your force is no longer big enough to overcome friction. Now, I got to be careful. Friction would shoot up instantly, bringing you to a stop, but as soon as you stop, friction goes back to zero. Otherwise, what would happen, let's suppose friction is 16 newtons, and I'm pulling with 10 newtons. Otherwise, what would happen is I would be able to pull and let go, and it would go shooting that way, because I have 16 newtons, 10 newtons, that's an unbalanced force that way of 6 newtons. Okay? So I don't want you to think that if you were pulling with 10 newtons and it went up to 16 newtons, that when you stop, friction is still 16 newtons. That couldn't happen. That'd be an unbalanced force in the opposite direction. It is unbalanced for a split second because it's decelerating. That's the force that's slowing you down and bringing you to a stop. Is that okay? I don't know why, Reed, but kids go friction loopy every time I do this. They start seeing it everywhere. And it is, but they start asking it to do things that it can't. So, D, it stops. It says explain your answer using principles of physics. I think we just did. Okay. So how do we calculate friction? This is also a formula on your formula sheet. Friction is mu times the normal force. Example 3. I think we're turning the page, yeah? A student gives an old shopping cart a big push on a flat, rough surface. You know what? Let's just think bad pavement, like you see in parking lots quite often. Okay? Which of the following is the best force diagram for the cart after the student has released it? Let me give you the same illustration, but instead of a shopping cart, we're going to use my little office chair. Instead of a really rough surface, it's going to be the linoleum here, but it'll still work. What we're talking about is, watch. Right now, right now. Okay? So before it came to a stop, while it was still rolling, but after it left my hand. Okay with that? It says, which of the following is the best free body rest force diagram? A, B, C, or D? What we're going to do is you're going to vote. A, B, C, or D. How high you hold your hand up is how sure you are of your answer. I'm positive. Pretty sure. Only voting because Mr. Dueck will make fun of me if I don't vote, and he'll damage my self-esteem because he's going to look at every face and keep track. Positive. Pretty sure. Best guess so that Dueck will leave me alone. Okay? So there's 4 free body diagrams. And again, we're talking about right then. Are you ready? Who says A is the correct one? 1, 2, 3, 4, 5. Who says, nah, people, it's got to be B? 1, 2, 3, 4, 5. Who says C? 1. Who says D? It's got to be D. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 26. Did you vote, sir? Jake? Did you vote?
Yes.
Did you vote, Kai?
Yes.
You did? Okay. So now, you can either attack someone else's answer as having to be wrong, or defend your own answer as having to be right. Attack or defend. Convince me. Who wants to try and convince me that they're right or that someone else is wrong? Kai?
B is right because forces come in pairs. And if it's moving forward, then it obviously has to have a force moving it forward, and there's a force pushing back, and gravity and friction are acting on it, and the normal force.
Okay, let's look at the verticals first of all. If you were drawing a free, you know what? Let's draw the free body diagram. Let's see what we get. So here's the cart. What are the forces acting on it? And you remember I always say, get the obvious one for a reason, because I want to start. Get the obvious one.
Gravity.
Okay. Is the shopping cart sinking into the ground like quicksand? No. Is it lifting into the air like Superman? So there must be balanced forces vertically, and this is what gave us the idea of the normal force. Okay. Kai, watch. What direction is the chair or the shopping cart accelerating? Think very carefully. What direction is it accelerating? Backwards, or in terms of here, in terms of left and right, to the? So that must mean if it's accelerating to the left, the net force must be pointing to the? Do you want to revise your answer?
I see it. Yeah.
What do you see?
The left arrow is smaller than the right one.
That would keep going at a steady speed at a straight line. That's outer space. And either this would be speeding up forwards, but it certainly wouldn't be slowing down. Oh, and what would D be doing? Well, the other one's accelerating. What direction? To the right. And that's not what's happening either. What's the correct answer? A. Now, I love the fact that people always want to pick D because you're getting velocity mixed up with acceleration. It's the same thing that happens when I throw a ball in the air. On the way up, which way is its velocity? That way. Which way is its acceleration, though? I'm telling you. It's the same question, I just flipped it 90 degrees. Okay? Oh, and what force is that pointing to the left? What would we call, let's finish my free body diagram. I didn't finish it. What force is that? That's friction. The gravel between the tires, that's friction. Okay? So those 5 of you that saw your way there, well done. And hopefully I've convinced the rest of you. It's funny, this is a tough one to beat out of you. You so want, if something's moving forwards, you so want there to be a force pushing it forwards. Those of you that take Physics 12 with me next year, I give you this same question, except now I put it on a hill. We push the cart uphill. And right away, as soon as the cart's moving uphill, kids want there to be a force. No! You just gave it a push and you let it go. It's slowing down still. There is no force up the hill. It's just coasting. There's a force down the hill because gravity's pulling it down the hill. This is a tough one to wrap your brain around. It's also interesting, my block B's, I had about 20 kids pick A right away. Does that mean they're smarter than you? I don't know. I think it means when in doubt, fall back to first principles of physics. It says explain your answer using principles of physics. We just did a good free body diagram. Is that okay? Now let's start applying this. I wrote for each of the blocks below, A, write a vertical force equation. B, find the force of friction. C, write a horizontal force equation. And D, find the acceleration. So what you're going to notice, Ben, is in a lot of the diagrams that I give you, if there's friction, somewhere in the diagram, I'll put a little value for the coefficient of friction. Here, mu is equal to what? 0.12. You know what that is? You know what? Actually, I think I have a chart of various coefficients of friction later on anyways. That's fairly slippery. That would be for you not comfortable to walk on in your shoes. You would already feel if you were walking on it that it felt a little strange. That'd be mud. Slippery mud, or a dewy grass, wet field, that kind of slickness, okay? You wouldn't feel totally comfy in your footing. So there's two situations here. Hey, let's do that. You know how we're going to start this before we do anything else? We're going to do a free body diagram. Absolutely. So there's the block. What are the forces acting on the block? Get the obvious one.
Gravity.
What else? Is this block sinking into the ground like quicksand? Is it flying into the air like Superman? Normal force. Then it looks like they gave us someone pulling. We're going to call that F applied. It's the applied force. It's equal to 20 newtons. It's someone pulling or someone tugging on a rope or a machine pulling. I don't know, Curtis. Something off stage is applying a force, though. So we just call it F applied. Which way do you think this block is sliding? To the right. So which way do you think friction's acting? To the? But I'll draw it shorter than applied because I'm pretty sure that applied is winning. I hope. Okay, A says write a vertical force equation. You know what? Normal force equals gravity. I could go winner minus loser equals 0 because it's not accelerating. You know what? It's a tie. Is that okay, Shaq? B says find the force of friction. Okay. Our new equation of the day is friction is mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? mg. You're going to find rarely will you know the normal force. However, if you've done a good free body diagram, look, you'll be able to find the normal force. You'll be able to find another force the same size as the normal force. This is why we do free body diagrams. So even though it starts out as mu times the normal force, I modify it to mu mg. And I got to be honest, Zach, in Physics 11, most of the time, the normal force and gravity will be the same, but not always. And in Physics 12, almost never. Every year I have kids come into Physics 12 and I say, what's friction? And they say, oh, friction is mu mg. And I want to take a baseball bat and just start swinging away at them. It's not. I've never said that. I will never teach you that. It's always mu times the normal force. Oh, and in Physics 11, the normal force, Curtis, will often be mg, but not always. Curtis, what does C want me to find? Oh, you know what? It said calculate the force of friction. I guess we should plug in numbers. I'm sorry, Curtis. Before I'll come back to you in a second. Friction equals, sure, Curtis, what's mu? I don't know, what's mu with you? Curtis, what's mu equal to? It's on the diagram somewhere. Go hunting for it. Yeah. 0.12. What's m? What's the mass? It's on the diagram also somewhere. Yep. And, oh, we all know, what's g? Really, people? What's g? 9.8, we're not including negatives because we're using our winner minus loser. We're taking care of the directions ourselves. I think I can do this in my head. 10 times 9.8 is 98. 98 times 0.12 is going to be 9.8 plus 1.96. It's going to be 9.8. It's going to be 10.8. It's going to be 11.76. Double check me.
Yes.
Yeah? Woo! So I guess you could make an argument. Well, I'm not going to worry about sig figs. Units. Friction is a force. Units. Newtons. Is that okay? Halen, what's C asking me to find?
Write a horizontal force equation.
See my free body diagram? Who's winning? Vertically, it's a tie. We don't care. Who's horizontally? Who's winning? F applied?
Yeah.
The applied force? Who's losing? Because it's in the opposite direction. We said our strategy is going to be winner minus loser equals MA. So it's going to be applied minus friction equals MA. There's my horizontal force equation. What did D want me to find? Emma? Oh, how would I get the A by itself in this equation? Yeah, just divide the whole thing by M. Oh, okay. So as an equation, it's going to be A equals applied minus friction divided by M. Let's plug in numbers. The applied was 20 minus 11.76 divided by 10. I can do that in my head. 20 take away 11 is 9. Take away 0.7 is 8.3. Take away 0.6 is 8.24. About 0.824? No? 0.824? Units, it's an acceleration. Are you starting to clue in, by the way, why I said it was worth memorizing what units go with what? It really cuts down on your thinking. It's an acceleration, so it's what? Will this accelerate? Yep. Not very fast, but it's going to move to the right. I'm a little more curious about the second situation, because in the second situation, some idiot's pushing down, increasing friction. I may find out that the applied force isn't big enough. Let's find out. How are we going to start this second situation? What's the first thing we're going to do? Take a guess. Free body diagram. Okay. What are the forces acting on this block? Get the obvious one. Absolutely. mg down. Is that the only downwards force? There's another one, I'll put it right next to it, of 15 newtons. I don't know what it is, but okay. Is this block sinking into the ground like quicksand? Is it flying into the air like Superman? So now, look. Why would this be, don't write this down, why would that be wrong? Sorry? Because what's this, you're right, but I need more, less pronouns, more nouns. The normal can't be the same size as mg, because if that was the case, I'd still have an unbalanced 15. It would have to be sinking into the ground like quicksand. You know what? In this case, I would be looking for, on your free body diagram, a normal force that was clearly bigger than mg, and I would exaggerate it. And again, this goes back to Otla's earlier comment. This is why for friction we said, you know what, it's not the mass actually, it's how hard the ground has to push back up. It's the normal force, which is affected by the mass, but also other stuff. Hey, what else? What other forces? Yeah, I'll come to that. I'll save that for last. What else? Oh, still an applied force. And friction. I've drawn friction smaller than the applied because I'm kind of guessing it's still going to move to the right, but I could be wrong. Okay. Ben, what did A want me to do?
Write a vertical force equation.
Okay, look at my free body diagram. What equals what? I'll give you a hint. Yep. Equals what?
mg.
Nope. Ah, what? Right? Has to. Otherwise, Newton's first, this is why we spent so much time on Newton's laws, by the way. Otherwise, Newton's first law says it would either be sinking into the ground like quicksand or flying into the air like Superman, or something would be happening. Have to be accelerating. It's not. I've seen boxes on floors before. They sit there quite nicely. There's my vertical force equation. Cool. Trevor, what does B want me to find? Oh, we have an equation for that. Friction is what times what, Trevor? What's our new equation of the day? Mu times the normal force. I don't know the normal force. Oh, but look. I know two other forces the same size as the normal force. See it? It's going to be mu, and then in brackets, mg plus 15. This is my new friction equation for this particular situation. Friction got bigger. Trevor, what's mu? I don't know. What's mu with you? What's mu, Trevor? So friction is going to be 0.12 bracket. What's the mass? 10 times, you know what? This is going to get lots of brackets. So let's go like this. Let's be clever. I'll make the outside bracket a square one, and then I can go 10, 9.8 plus 15. Yeah, that looks better, yeah? Which is what? Mr. Dueck, why don't you do that one in your head? Okay. Well, it's going to be 11.76 plus 1.8. 98 plus 15 is going to be 108. It's going to be 113 times 0.12. It's going to be 11.3 plus 2 point. It's going to be 13.33. No, I'm off. What is it?
13.56.
Ah! Oh, great question. You would go like this. 0.12. Who asked me this? Okay. Bracket. You might need a times. I don't know, but my calculator clues in. Then I would not use. I never use brackets to show something times something. I only use brackets for the grouping part. So I would go like this: 10 times 9.8 plus 15. And if you had a teacher who went on a rant about getting a good calculator at the beginning of the year, and I hope you all did, your calculator should do all of the order of operations just fine. And you should get the 13.56. So in writing, I show multiplication with brackets, and the reason is a times looks too much like an X from math, and the dot looks too much like a decimal. So I avoid the. Also, by the way, in physics, that means something totally different from that. They're totally different operations. One's called a cross product, and that gives you a vector answer. One's called a dot product, and that gives you a scalar answer. You'll learn that in first year university physics if any of you take that much. Anyways, so I'd use brackets in handwriting, but times on my calculator, because this does not look like any physics symbol. Okay, 13.56. Units, it's a force. Newtons. By the way, can you tell me, will this thing still accelerate? It will. When wouldn't it accelerate? If friction was bigger than 20, because 20 is the applied force. If we'd gotten a friction force of like 22, we wouldn't be saying that friction was equal to 22 in the opposite direction. We would be saying friction maxed out at 20 and quit there because it's a reactive force and the force causing it is applying with 20, so we only got 20 in the opposite direction. Otherwise, we'd have unbalanced forces. Being technical here. C. C wanted the equation? You know what? It's going to be the same. Applied minus friction equals M, isn't it going to be the same horizontally? Winner minus loser. I don't care about, I'm not putting verticals into a horizontal equation. Right? And Kurt, what was D asking me to find, Curtis? Oh, how would I get the A by itself? More specific. Divide by what? How do I get this A by itself here? What's in front of it?
M.
Yeah. So how will I move the M over? Divide. Yeah. We're going to get the acceleration is going to be the applied force minus friction divided by the mass. It's going to be 20 minus 13.56 divided by 10. Now this I can do in my head because 20 take away 13 is 7, take away 0.5 is 6.5, take away 0.6 is 6.4, 0.644? It's really just dividing by 10. It's nowhere near as tough as it sounds. Units. It's acceleration. Yeah. By the way, I didn't in this question, but if I wanted to make this a nice longer test question, as a part E, I could say, assuming VI is 0, how far will it travel after 3 seconds? And now you could go D equals VIT plus a half AT squared and get a distance. Or I could say, find V final after 8 seconds, and you could find a V. All the last unit stuff. Now that I got an acceleration, now I can bring in all my last unit stuff too. Kind of cool. Turn the page. There is actually 2 types of friction. Now, we're going to pretend this year and next year that there's only one type to make the math easy. How many of you ever slid or pushed something across the floor that was really stinking heavy? I mean, like you had to really work at it. Did you notice once you got it moving, it was easier to keep it moving? It's getting it moving. See, those are the 2 types of friction. There's something called static friction. That's when an object is standing still. And there's something called kinetic friction. Once you get it moving, actually mu gets a bit smaller. The objects get a bit slipperier in relation to each other. So there can be 2 types of friction. Look at this. It says this. There can be friction on an object even when it's at rest, since those hills and valleys, those microscopic hills and valleys, lock up. They fit into each other, kind of like a jigsaw puzzle. The force of friction on an object at rest is called static friction. This is me being a nerd. I'm going to show it to you, but I'm not going to test you on this. So let me give you example 6. Let's suppose I pull on a desk with a force of 2 newtons, and the desk does not move. Which of the following is true? A, static friction is greater than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. D, there is no static friction. You know what? Once again, I think this is a chance for us to vote. I think once again, how high you hold your hand up is how sure you are of the answer. Positive? Pretty sure. Oh, I don't want Dueck to make fun of me. Okay. So again, if you pull on a desk with exactly 2 newtons of force, which of the following is true? Who says A? 1, 2, 3, 4, 5, 6, as peer pressure takes us. 6? Oh, let's change colors, Mr. Dueck. So, who says B? 1, 2. Lots. Who says C? Who says D? Okay. Convince me. Sorry, A people. Why must A be wrong? Yeah, Shaq. If it was greater than 2, I'd have unbalanced. In fact, if it was greater than 2, what you could do to move anything is you would go like this. Let go, and it would knock you guys over and go shooting back against you guys. Because there must be an unbalanced force and it must accelerate. It'd be kind of a weird world, kind of a strange universe. So don't think it can be that. What if it was less than 2 newtons? So, okay, it would have to be accelerating towards me. That's what happens anytime you do, sorry guys, you do slide something. You just overcome the force of friction. So that can't be right. Oh, and I'm pretty sure there is friction. Okay? Explain your answer using principles of physics. Since A equals 0, F net has to be 0. What do 3 dots like that mean? Therefore, friction has to equal applied. You might even do a free body diagram if you really wanted to impress me, but it's got to be a tie. So static friction acts when you have 2 objects at rest relative to one another. Okay? As an example, Dan, you want to hold your calculator, but get your hands up off the desk. I'm going to lift the desk. Hold your calculator. Sit down. Just hold your grab your calculator. There you go. Grab your pen. Grab this. So I'm going to lift this table up, and this is not going to slide. Now gravity is pulling it down the hill, but there's enough friction between this binder and the table, static friction because it's not moving, to hold it in place. Of course, I can increase the component of gravity, and eventually, I just applied a downwards force bigger than static friction could overcome it, except it got caught on the corner. This is what happens when you apply a parking brake on a car on a hill. Static friction. Okay? A block of wood or a binder will remain stationary as you increase the angle until you hit that magic moment when the gravitational force down the hill is bigger than static friction up the hill, and now it'll start to slide. Okay? The force to overcome static friction, this goes back to my comment. Some of you said, when I moved something really heavy, getting it going was tough. Static friction is always bigger than kinetic friction. Kinetic friction is once you get it moving. And the reason is, how many of you have ever been on a really bumpy gravel road in a vehicle before? When you go faster, is it smoother or bumpier? I think there comes a time, Valoria, if you go fast enough where it starts to smooth out a little bit. Why? You've been on gravel roads, have you not noticed this? Like if you go really, really slow, you feel every single pothole. If you're going at about 3 or 4 kilometers per hour, yeah, you feel yourself go down into each and get up. Why don't you feel it quite so much if you go quicker? Sorry? You know what? Your tires don't have time to drop all the way down into the puddle. It's the same thing with friction. We talked about those molecular jagged hills and valleys. If you start sliding it faster, they still interlock, but they don't have time to completely lock up. They're kind of skimming across each other. That's why once you get something moving, it's easier to keep it moving. Kinetic friction is always slightly less than static friction. To keep the math nice, we're going to treat both types of friction as the same thing. So I've explained, because you've probably noticed that, why it is easier to keep something sliding. Getting it sliding is tough. That's why. Oh, got a little video for you. Here's a little kid who understands friction. Next page. Here's some coefficients of friction. Here's some mu's. Wood on wood, not really sticky. It's got a mu of about 0.25. It's got a coefficient of friction of about 0.25. Steel on steel, not very slippery. This is why we have to add lubrication or oil to motors. Steel on steel actually has a fair bit of friction if they're rubbing against each other. It generates lots of heat. It's got a coefficient of friction of about 0.5. But it goes down to about 0.1 if you add oil. That's why we add oil to motors. Doesn't get to 0, but we can get close. Rubber on dry asphalt, anywhere from 0.4 to 0.7. It's better on, I think I gave you rubber on concrete. Concrete's a little stickier than dry asphalt. Rubber on wet asphalt goes way down. So slow down when you drive, because since friction is smaller, that means that your acceleration has to be smaller, which means it's going to take you longer to come to a stop. It has nothing to do with your skill. Rubber on ice, anywhere from 0.005 to 0.01. Steel on ice, about 0.01. And these are rough. There are other factors that affect it as well, but just to give you an idea. Can you have a coefficient of friction greater than 1? Glue can support its weight and something else's weight. Actually, not just glue, by the way. What force makes a car go forwards? What force is it that pushes your car forwards? Do you remember from the beginning of this lesson? What force is it that pushes a car forwards? Friction. So dragster tires have a coefficient of friction bigger than 1. They're very expensive tires. They're very, very sticky, which at first might seem counterintuitive. You might say, well, wouldn't they stick to the pavement and slow it down? No, no, no. It gives you a big force of friction. And what force is it that pushes a dragster forward? Friction. Okay. As a matter of fact, the reason dragsters always do that smoke show before they do the race, they're not doing it to impress the crowd. They're heating the rubber up. What's stickier, cold rubber or melted rubber? Let me ask that with physics terms. What has a higher mu, cold rubber or melted rubber? Melted rubber. So what has a higher force of friction, cold rubber or melted rubber? Melted rubber. So what will push a dragster faster, cold rubber or melted rubber? Okay, it's all physics. The byproduct is people in the crowd like the smoke show. I don't know if you've ever been to a drag race, but they'll do a smoke show beforehand. They're melting the rubber. Example 7. A force of 120 newtons is needed to push a box along a level road at a, that's an important word there, steady speed. If the force of gravity on the box is 250 newtons, what's the coefficient of friction between the box and the road? You know what this question is asking? It's asking, what's mu? I don't know, what's mu with you? It's asking us to find mu, the coefficient of friction. Any suggestions on how we should start? Here's our box. What are the forces acting on it? Get the obvious one. Is this box sinking into the ground like quicksand? Is it lifting into the air like Superman? Are there any other vertical forces mentioned? In other words, they're not trying to pull a question like this one here where we had that fit. Does it mention like a force down or a force up or an extra weight or anything like that? Then you know what? I think we can safely and reasonably draw the normal force same size as mg. What else? There is friction. We'll come to that later. Tony? Oh, the first phrase says a force of 120 newtons. You know what? And I'll even tell you how big that is. It's 120 newtons. We're pushing with that. We're applying a force of that. And Darian, what did you say?
Friction.
How big should I draw the friction arrow? Y is smaller than the applied force. Sorry, wrong. What word did I underline? What words did I underline? Which means actually I think friction is exactly. And this is when you folks have moved something really heavy like the wrestling mats. What you do is you get it going at a constant speed and you just keep it going. What you're really doing then is the force that you're pushing with is exactly matching the friction force in the opposite direction. Okay. Vertically, it's a tie. Let's write a horizontal force equation. Who's winning? Well, technically no one, because it's steady speed, but it's moving to the right because that's the applied force. Let's call that the winner. So let's go like this. Winner minus loser, because friction is in the opposite direction, equals MA. Yes? Cool. Oh, except what 2 words did I underline?
Steady speed.
So really I have this. Applied minus friction equals 0. Although, Emma, I think a nicer way to write that would be just to take that minus FR and plus it over to the other side. I think what I could really say is yeah? Okay. Friction is what times what? So you know what? I can write this as F applied equals mu times the normal force. What's this question asking me to find? The coefficient of friction, which is what in this equation here? How would I get the mu by itself? I guess divide by F, because the Fn's multiplying, I guess divide by Fn. So if I hear you correctly, you're saying the coefficient of friction is going to be the applied force divided by the normal force. It's going to be 120 divided by, I don't know the normal force. Oh, but look. I know another force the same size as the normal force. And what did they tell me the force of gravity was? They actually didn't tell me M. They just said the force of gravity on the box is what?
250.
They gave me mg. That's going to be 12 divided by 25. 0.48? No, what is it? 0.48 even? 0.475? Oh, 0.4897.
I got 0.4.
I think 12 divided by 25 is, yeah, 0.48. Yeah, right? Whew. Units. A lot of kids want it. Newtons, Mr. Dueck. No. What did we put on top here? What's that 120 measured in? Newtons. What's that 250 measured in? Newtons. What's newtons divided by newtons? This is why we said the coefficient of friction has no units. Because if you ever try and get it by itself, trust me, the units will cancel. It's a unitless, dimensionless ratio. 0.48, you know what? Close to steel on steel or rubber on dry asphalt, if you're trying to put it into context. How many more am I doing here? Okay, we're going to go like this.